we move to the next speaker, Omar Jesús Franca Santiago, from the University of Kassel. Okay, so
yes, so thank you.
You can start to share.
Okay, thank you, Eduardo. So let me share my screen. So first of all, I would like to thank you the invitation to speak here, and I'm very glad to hear some people in the audience that I know.
Okay, I think there's a problem with the project, the sharing the screen.
Let me check again. So does it work at the moment?
At the moment, yes.
Okay. And now, no.
Apparently the full screen doesn't work.
Yeah, so let me check again. Now?
Now it's working.
Yes, it was a problem with my Adobe. I do not know. Okay, so once again, thank you very much for the invitation, and I'm very glad to see people in the audience that I know. And also, I'm very glad because this kind of online meetings helps us a lot in order to erase the frontiers or the boundaries between our countries, and we could speak even that we are in several different times. So let me start. So the outline of my talk would be this one. I will speak about, I will give you a brief introduction about the things that I'm working at the moment. So first of all, I will speak mainly about the transition radiation here in topological insulators. So I will give you this brief introduction because I found really nice the previous talks given by all the professors. So, and I will give you this briefly introduction regarding my current research at the University of Kassel from my first year of postdoc here. Then I will give you a motivation on how to study, why to study this transition radiation in these interesting materials. Also, I will focus a little bit in the formalism that we employ to study this electromagnetic response, which is the so-called theta electrodynamics, which is an effective field theory that models the electromagnetic response of these materials, also from the magnetoelectrics. And then we move on to the transition radiation stuff, and then I will give you some conclusions and then some future views in this work. So first of all, there's a lot of importance on these topological terms, mainly in quantum field theory. There are a lot of things regarding the anomalies, and these papers are the seminal papers coming from Atla, Bell, and Yakiv, which brought to the table the chiral anomaly, and they explain the importance. And then there was a lot of people that worked and connect this anomaly with the topological terms. Also, a couple of decades later, after the discovery of the quantum Hall effect by von Klitzing, this Haldane also explained it a lot with his model, and he established the connection between this important effect also with the topological terms. And another important thing is that these topological terms bring the modification in the field theory that we are studying. And also it's important to know which is the dynamical behavior of them. So in this framework, the topological magnetoelectric effect is very important, and as we will see below, it comes from the addition of an additional term to the Maxwell Lagrangian, and at least in the effective field theory, and it models this important effect for these kind of materials from an effective field theory point of view. Another important consequence of this in this framework of the dynamical behavior is that we, at least from the condensed matter point of view, we can obtain observables that actually are measurable in the laboratory. For example, these quantized Faraday and Kerr rotations and so on. So my main motivation, well, there are several motivations. So probably the main motivation from my side is that during the PhD, my PhD at the end, we discovered, or we found that these materials that present reversed Vavilov-Cherenkov radiation. So previously, only in 1968, a Soviet guy, which was called Veselago, obtained in calculations and in his article that this reverse Vavilov-Cherenkov radiation will only appear in left-handed materials. But we found that this interesting effect can also be present in these three-dimensional topological insulators, which are ordinary right-handed materials. So what does that mean? That the triad between the magnetic, the electric fields and the wave propagation vector are right-handed or left-handed. But in this case, for topological insulators, is only a right-handed material. So that's an interesting result that we obtained. So here I showed you this nice plot, because here you could see in this black arrow that from this point is the particle, let's say, which comes from left to right. And here in this line from pi over 2 to 3 pi over 2 is the interface between two magnetoelectric media. And in this part, in the left side, in the right side, it could be this material, which is a topological insulator, this in pink. And in the left side, which is here in the side of this point, it could be an ordinary dielectric medium. So when the particle comes from left and crosses the interface, it appears a typical Cherenkov cones, which are here plotted in blue and in purple. And immediately in the backwards region, in the backwards direction, it appears also these two cones, these backwards cones, which are also the Vavilov-Cherenkov typical cones, but now in the backwards direction. As you could see here in the main plot, here with the big circle, these backwards cones cannot be seen, but one has to make a zoom here in the origin to see them. But at least we found that with the current measurements it can be obtained in the laboratory. So here you could see both with different velocities. So that's one of the main motivations here. So this is the Cherenkov effect, and also this reverse Vavilov-Cherenkov effect too. So the transition radiation will constitute the next step on complexity in these configurations. Also, the next motivation, which is really, really effervescent at the moment. At the moment, there's the experimental physicists are at the moment very, very busy on thinking and researching on how to detect dark matter. There's a lot of candidates for dark matter, but one of them are the axions, and they are well motivated. And here in this review, you could find a lot of candidates, and mainly these axions. So as we have seen in the previous talks, there are a lot of connections between the axion electrodynamics and also these materials. So people posed or asked if these materials could serve us to detect these axions. Therefore, there were several research, for example here, that try to use topological insulators to detect these axions. Also, these are the same, these two articles are from the same group in Germany. They also take topological insulators, but they doped them in an antiferromagnetically way. And very recently, during my last calculations of the current of my current research, these persons in Stockholm used another kind of materials which are quite related to this magnetoelectric response, which are called multiferroics. So as you can see, there are a lot of people researching and trying to ask if these materials could serve us to detect these axions. So these are my main motivations, and then we proceed to continue. So first of all, I will focus myself, I will restrict myself to an effective point of view. So this is motivated, or this effective field theory comes from the axionic electrodynamics, which was first proposed and theorized by Wilczek at the end of the 80s. But in our case, and making a connection with the microscopic point of view, we will integrate all over the fermionic degrees of freedom. For example, in the microscopic degrees of freedom that we saw in the talks of yesterday, and also in the previous talks from today, and this leads to this additional term here at the third bullet point, which comes from this integration of the degrees of freedom. This was also has been well studied, and also this effective field theory, which models the electromagnetic response from the topological insulators, can model the electromagnetic response also for magnetoelectrics. And so the Lagrangian for this theory is the following. You take the Maxwell Lagrangian and you add this term, and to making connection with the topological point of view, this electric field, which is E dot magnetic field B, is the abelian Pontryagin in 3+1 dimensions. We coupled it with this theta, which is in axionic electrodynamics is the axion field. But in our effective field theory, in order to model the electromagnetic response from these topological insulators or the magnetoelectric media, as I said, we restrict this theta field to this form, which will have a constant value, theta1, times this Heaviside function, and in the lower semi-space, we will have also a constant value, theta2, times the corresponding Heaviside function. This is a schematic pictured or depicted here in this small picture here in blue. We will take a magnetoelectric medium with permeability, with permittivity, and also with this topological parameter theta1. In the lower layer or in the lower semi-space, we take also a different permeability, a different permittivity, and a different topological parameter. We will, for the moment, we will think that the particle or that the sources will be in the upper layer. So this is the so-called theta electrodynamics that we dubbed in this way, just to make a difference between the axionic electrodynamics and the theta and this effective field theory. So the modified Maxwell equations that come from this Lagrangian are here. So in green, I wrote the inhomogeneous Maxwell equations that are modified after this presence of the topological of the interface and due to the additional term. And in the other two equations are the homogeneous Maxwell equations that remain in the same form. That could be also proved or could be deduced from the Euler-Lagrange equations. And if you compute the Euler-Lagrange equations, you could also find that the Bianchi identities remain the same. So therefore, these two equations which come from the Bianchi identities are untouched. Or in green, there will be new contributions. So here, JE is the external current, and D is the displacement field, and H is the magnetization field. So another way is to propose that there are constitutive relations for these materials, and here are there. So these are the electric field times the permittivity plus the magnetic field times the axion field plus a polarization, a noisy polarization, and the same for the magnetization field, which is these three terms. But here it comes a minus sign, and in M is the noisy magnetization. So these two additional terms are modified and model the absorption of the material. But for the current study, we will not take them into account. So if one substitute explicitly both fields D and H here in the modified Maxwell equations, one could obtain one could split them in terms of the E and in the B field, and one could read how the current density and the charge density are modified. Also, an important thing here is that this effective current and these effective charge densities will depend explicitly on the also in the axion field, but explicitly they will be time they will depend on the fields on B, on E. So another important thing here is how the boundary conditions are modified. Assuming that the time derivatives of the fields are finite at the interface, one could obtain the boundary conditions that are modified in this way. And again, in green appears a modification due to the presence of this additional term that we have added to our Lagrangian. And this is proportional. This is proportional to this topological parameter that we labeled as delta, capital delta, and which has this form for magnetoelectrics, for a generic magnetoelectrics. But in the case of a topological, when we have a normal dielectric medium and in the other layer a topological insulator, this delta, capital delta, takes this form with M an integer, and M encodes how the material is gapped, how the both balance, the balance and the conducting band are gapped. So this is very important, and everything is encoded in this topological parameter. That's the idea on performing an effective field theory. So also important to notice is that everything I have that I wrote is in the Fourier space, because that will be important for the next calculations. So now in my talks, I would like to expose an illustrative example on how this formalism works in order to gain more insight or physical insight on how these materials work. So let's imagine, again, everything is in planar symmetry. Let's imagine a topological insulator here in green, and in white a normal dielectric. This picture is taken from this nice article, which is in Science. So the idea is to put in front of this planar interface a charge particle, a point-like charge particle Q here, and through the image method, one would like to solve the configuration and obtain the electric and magnetic fields. So after performing that, one obtains the typical point-like electric field, which is the first term here, but now appears in green an additional term. Also, I would like to remark that these expressions are only for the case when both permittivities have the same value, and also when the permeabilities are equals to 1. So in the upper layer, it appears, as I said, the normal electric, the point-like electric field, plus this additional term. You could see that this, the only difference came from this plus here in the vectorial dependence, and this term with the squared delta could be interpreted as the effective image charge. And also, if one would like to study the electric field in the lower layer, one obtain this electric field in green, and it appears also this image charge here, this effective image charge. So when one study all the electric field in all the space, one have to take into account both expressions, and they are well behaved. So what it says here, an important thing is that this picture is not complete accurate unless we also solve the remaining equations, as I told you here. From the boundary conditions, the magnetic field and the electric field are not independent for these boundary conditions. So that means that an electric field will induce a magnetic field, and the magnetic field will induce an electric field. That's the reason that when one solves through this image method, that the image method that we studied in the graduate school, we obtained also this magnetic field in pink, which is quite interesting because this magnetic field is related to the magnetic monopole field. Both electric and magnetic field have the same vectorial dependence, but as you could see here, this prefactor here and this prefactor here in the upper layer and the lower layer could be interpreted as this G, which appears here in this picture, which is the strength of the magnetic monopole. That's interesting because in comparison with normal dielectrics, which also can one could obtain an image charge in order to model the interface between two different dielectric media. These materials in our image method can be interpreted as the sum of a normal as a physical charge plus an image charge particle plus the field of a magnetic monopole. I would like to emphasize that the images method, it's very illustrative, but unfortunately they are only mathematical tools, so just to fix ideas. Once the magnetic field is obtained, one could ask what happens, which could be the current density that generates this magnetic field. So because everything is time independent, one takes the curl of these magnetic fields and one obtains this nice current density, which is not another thing than the whole current density. And why? Because this lives only at the interface here at c equals 0, and the vectorial direction is in the direction of the unitary vector phi. So that's how these materials could work. Then let's move on the next step. So unfortunately, this image method or solving directly the boundary conditions needs a lot of effort because it does not work, or it is not easier to solve them when we have arbitrary currents which does not respect the symmetry that we have. So the idea is to go further, and then we will employ the Green's function to overcome this task. So from the inhomogeneous Maxwell equations, we could, and taking into account naturally the constitutive relations, we work with them, and then we could obtain this inhomogeneous Helmholtz equation. The normal or the standard Helmholtz equation for the electromagnetic field does not have this green term. But for our case, this green term is really important because all the electromagnetic response of these materials will be encoded here. So important to notice here is that this expression tells us that if the axion field is homogeneous, that means that if it does not depend on the position, this term will be 0 and we will recover the standard Helmholtz equation. And now this current density is the sum of the noise current density plus the external field, the external current density. So as I told, told you, this noisy current density models the absorption of the material, but for our current talk, we will not take it into account. So the solution of this inhomogeneous Helmholtz equation is through the Green's function is this one. So here is this current density contracted with the Green's function, which is now a which is a tensor, and one obtains the electric field. So you only have to give one or the current density. Once the Green's function is known, we will obtain the electric field, and we could study everything once this electric field is obtained. Again, everything is in the Fourier space. So, and also it will depend on how to solve the related integrals. Important to say it's are the characteristics of the Green's function or of the Green's tensor. This Green's tensor G for our configuration can be split into reflective and transmissive part. The reflective part will be in the upper layer because we will put the source at the, in this upper layer. So this reflective part will have two terms, the free space Green's tensor plus the reflective part. And in the lower layer, we will have the transmissive part, which will only have the transmissive terms. So also another feature of this Green's function is that there will be the Fresnel coefficients that we are very familiar with them will be modified. So in green are the modifications. If you take delta equals 0 to recover the standard case, they are gone, and when we recover the standard Fresnel coefficients. But as you could see, they are more complicated, and also very important to notice is this modified Fresnel here, the second one, which is a crossed term because it mixes the polarization or the normal modes of the standard electrodynamics. So
Omar, I'm sorry. What is
yes?
omega mu?
Omega mu is here below. It's
there. I'm sorry.
It's the product of the permeabilities and this dependency here.
Okay, sorry, I didn't see it.
Okay, so also everything will depend on the propagation on the z component of the wave vector, which is here kc, 1, which labels which if this wave vector is in the upper or in the lower layer. So that's also an important thing. Another important fact due to the form of these modified Fresnel coefficients is that if you swap the labels 1 to 2 and vice versa, they are not equal. So I mean R12 TM is not equal to R2 to R21 TM. So that is another consequence of these materials, and in another frameworks in optics, it's called the non-reciprocal media because they do not respect the well-known relationship that Green's functions, when one swap the primes variables to the non-primes, they are equal. So in this case, for this kind of materials, this relationship will not be held. Well, that's all about the Green's tensor, which is the kern, which is the seed of this, the main tool of this work. So let's move on finally to the transition radiation. So what is transition radiation? As I tried to explain at the beginning, it's the next step on complexity in comparison with the Vavilov-Cherenkov radiation. Why? Because we now have two different permittivities. So, and then again, it's due to a charged particle that travels with constant velocity, and it crosses the layer, which is here in this thick black line here, and it crosses through the region U2. I would like to stress that this is important to know that in the graduate school, we learned that a charged particle moving with constant velocity does not radiate. But it's always surprising that it took a lot of time for the humanity, concretely to Cherenkov and to Vavilov, and also for these two guys, which is Ginsburg and Frank, at the beginning of the 1930s of the last century, and in this year, 1946, to break that paradigm. So you could say that this charged particle has constant velocity, but it is still radiate. So the current, let's move on. So the current density of this, for this configuration, is the same as in the Cherenkov case, but here we will take an infinity path. And also another important ingredient for this transition radiation, it's that we will focus only in the backward radiation. That means that the source is here, and we will put the observer or our detector in this upper layer, which is labeled here as U1. The particle, as I told you, crosses the interface towards U2. And in U2, it could be possible that the Vavilov-Cherenkov radiation and the transition radiation can occur at the same time. So in this way, to rule out the interference or the hybrid radiation that could arise, we will restrict the velocity of the particle to be lesser than the minimum between the light velocities of both media. There are also a lot of studies about how one should study this interference between both kind of radiations. So then, as once we have the external current density, then one only have to plug them into this expression here and to solve the integrals. Unfortunately, the integrals are not so kind and to solve. So, and there is no an exact solution for them, but fortunately one can solve them through the steepest descent method, and one should also perform some approximations to them. And particularly, we are interested in the far field approximation, so we have to employ it. And after employing this steepest descent method together with the far field approximation, what obtained this long expression here, which is the electric field here. So first of all, there are two contributions for our electric field. The first one is this in green, which is the lateral, which is an electric field, but due to the lateral surface waves, which are very restricted to the interface, and we will not study them here, but they decay very quickly outside the interface. But for transition radiation, the important contribution is this long term from here, which, as you could see, is due to spherical waves. The modifications in comparison with the transition radiation in the standard case are coming in green also here, and are encoded in the modified Fresnel coefficients. And also it appears a new term here, which propagates in the phi direction. That means that there are two contributions that travel perpendicular to both of them. And at least in the electric field, these expressions for the crossed Fresnel coefficient are linear in the topological parameter. Another important feature here for this electric field are the denominators. The denominators have a very familiar form, and if you could remember from the Cherenkov radiations, there are indeed these kind of terms. So here is the velocity beta, is the ratio between the velocity of the particle and the light velocity, and here appears the typical cosinus. So another important thing here is that when the denominators here could be 0, they will diverge and they will reproduce the Cherenkov radiation. But as we have restricted to velocities lesser than the light velocity in both media, this will not happen. Another important thing to say is that there could be also applied here the image interpretation, but we will take them in the next slides. Another thing to say here is that everything is described in with θ1, which θ1 moves or is only in the upper layer. But here you could see that I wrote a θ2 because θ2 can be expressed in terms of the θ1 through the Snell's law. With this picture of the electric field, we can move on to compute observable quantities. So as I told you, everything in this framework is a right-handed triad between the electric, the magnetic field, and the wave propagator. And that could be seen here if you take the scalar dot product between this electric field and the direction of the wave propagation, which is parallel to the radial direction, everything goes to 0 regarding when one ruled out the lateral waves, which are not important for the radiation that we are going to study. So let's take some approximations here. Until this point, everything works quite well for permittivities and permeabilities that depend on the frequency also. But from this point and henceforth, I will restrict to constant permeabilities and constant permeabilities. That allows me to obtain this expression for the angular distribution of the radiation. And here I showed you the results for the polar plot, which is in the left side for this transition radiation. And for these parameters, let's mention that the interface is located at this line, P/2, from P/2 to 3 times pi/2. The particle is moving from right to left, from this point here to left. And also the standard dielectric with the levels 1, epsilon 1, and mu1, it's in this left side where the lobe appears. And the topological insulator will be in the other side where the lobe does not appear. Which topological insulator are we studying is this one, and whose name I do not dare to pronounce. And in green, you see the typical pattern, the polar plot for this material. And in purple is the standard case when the topological parameter is turned off. Both cases are for this velocity, which is 3/4 of the light speed. And here in the right side, you observe the standard plot. So from both of them, we could conclude that they are almost the same and the difference are not significant. But if we move on to the ultra-relativistic regime, and instead of a topological insulator, we change to a magnetoelectric, a concrete magnetoelectric, which is this one, we see clearly from both plots that there arises a appreciable enhancement between both radiations, between both angular distributions. And you could see that both maximums are in accord with the between both of them. So these are the parameters. Again, it's vacuum. The interface is between vacuum and this magnetoelectric, which, as far as we know, has the greatest topological parameter, which is 0.22, which is rather big in comparison with the previous one, which is 11 times alpha, which alpha is the fine structure constant. So that's an important result. And here one could also apply the image method in order to understand why this enhancement appears. So again, the particle comes here, which is the physical particle, and crosses the interface, which is here. But also it appears the image particle with the moving in from the inside the medium, but the additional contribution will come from the magnetic monopoles, the image magnetic monopoles that come from the second media and the first media that are going towards the interface. And because the angular distribution is the squared, the modulus of the electric field, it will be of order of a squared capital delta. That's the reason that this enhancement comes. Obviously, it depends on how big is this topological parameter. And then obviously one could ask, how about if we swap the situation, if the particle comes from the left and goes to the right? And here I show you the opposite situation. And here we found that there's no significance between them. So we also found that numerically there's no difference between them. So that accounts for the directivity of the phenomenon. This directivity means that it's not the same that coming from the first medium towards the second medium. It's not the same situation that if you come from the second media towards the first one. And here, the topological parameter seems to not to play. So that will be quantitatively explained in the next slide when we tackle the problem on how to obtain the frequency distribution in this ultra-relativistic regime. Again, let's take the vacuum interface and the vacuum to TI case, but additionally, let's take that the topological insulator is a non-magnetic one. When one performs this choice, and together with the ultra-relativistic regime approximations, which is encoded here, which means that the main contribution is focused only in small angles, one obtains this small expression for the frequency distribution. Again, in green, I put only the modifications in comparison to the standard case. And here, this F, this curly F, you could see, is only the sum of the modified Fresnel coefficients, which are explicitly here shown. And if we, again, swap the situation, that means that if we go from the TI to the vacuum, and again, from for a non-magnetic topological insulator, we obtain this expression, which is the same as in the standard case. And here is explicitly any dependence on the topological parameter. Also here, it's this approximation employed because we are now in the opposite situation. That means that we are in the topological insulator moving to the vacuum. That means that the light speed is not C, it's C over the refraction index of the medium. That's it's translated in this condition here. That means that we are respecting the choice that the velocity of the particle does not overcome the threshold of the Cherenkov radiation. So that's what I describe here in pink. Important that this frequency distribution does not depend on the topological parameter. And also very important to say is that both of them have the same logarithmic dependency on the velocities as required from the standard case, which was first obtained by Garibian a long time ago. So important now is to ask if everything is fine, so we can ask for a consistency checks. For an observer in the upper layer, again, we could ask or we could study this first limit case, which is when we turn off the topological parameter and we send the limit when both permittivities are the same. When one makes that limit, one obtains that everything goes to 0. So that means that there is no transition radiation. Then it's a first consistency check. The second limit case is what if epsilon is equal to epsilon 2? That means that both the electric media, it's a single one. But what about if capital delta is not 0? That means that we have a standard dielectric in the upper layer, or in the lower layer, we put a magnetoelectric or a topological insulator with the same permittivity of the upper one. After these choices, we obtain that the angular distribution takes this form. So again, everything is new. It's quite important to appreciate here that everything is proportional to the capital to the topological parameter, but to the square of this parameter. So in blue, we observe again the typical Cherenkov denominator, which again, when it is 0, it diverges, and again, we obtain the Cherenkov radiation. If additionally, we want to obtain the frequency distribution after putting a non-magnetic topological insulator, and after integrating over the solid angle, we obtain this short expression here in pink. From both of them, you could see that even when both permittivities are the same, there will appear transition radiation. This is an important difference between this configuration in comparison with the standard case, because in the standard case, there is no choice. One have to take different epsilons in order to find this kind of radiation. But here, the delta or the topological parameter, it mimics this, mimics the role of the permittivity. So then I'm going to my conclusions. So the grain function approach, together with suitable approximations, allowed us to obtain analytical forms to study the magnification of the electromagnetic radiation in presence of topological insulators, but also for magnetoelectrics. The enhancement for the vacuum to TI case for an ultra-relativistic particle could be relevant for dark matter detection. And it would also offer an important or indirect measurement for this topological parameter. That's also a desire of the community, but unfortunately, these results only offer another indirect measurement of this topological parameter. The community would like to measure this topological parameter directly in a clean way. We tried to do that, but it's only an indirect measure of it. And another conclusion is that the transition radiation, we have found that this radiation can exist even though the permittivities of the media are the same, but only by retaining that one of both media have a topological parameter different from 0. So, and the future work that Stefan and I are currently thinking and working is that everything regarding the TIs could also appear, at least in the perspective of the magnetoelectric effect for chiral matter. So the idea will be to analyze also if this chiral matter could enhance these effects, but for arbitrary incidents, because at the mainly at the main beginning of my talk, I showed you also the case for the Pavlov-Cherenkov radiation, but everything is for normal incidents as well as this transition radiation. But that means that everything respects the azimuthal symmetry of this configuration. But what will happen when we, instead of a perpendicular or a normal beam for these particles, instead of that, if we put a parallel one, but very closer to the interface, which could be the effects of that. And this is mainly motivated because at the Universität Kassel, there's this important institute also, which studies the molecular chirality and its interaction with light from the theoretical and experimental point of view. That's also the reason that we are also moving on to study these phenomena in the quantum case, which are also another research lines that we are currently working. So in this direction, as I showed you, here appears also lateral waves, but we have ruled them out from this configuration. But if we change from normal to parallel incidents, how relevant could be the lateral waves? That's a question that it's at the moment we are studying. With that, I came to the end of my talk, and then I would like to make some acknowledgements to Stefan, which is my current mentor, and his group. and also to Conacyt, which has through its grants, I could perform my first and also my second year of my postdoc here. So thank you.
Okay, we thank Omar for the nice presentation. Then there's time for a few questions. Are there any questions? Oh, meanwhile, I would like to ask one question about the physical meaning of this noise magnetization and noise polarization that you show in the constitutive relations at the beginning. It's curious. I am curious why you insert this.
So this noise polarization and magnetization, the idea of them is to model through a Langevin dependency the absorption of the media. So that's only the thing that we add this polarization and this magnetization here. So in this way, we could split the noise contributions due to the lattice, let's say, from the material, from the external sources. That's the idea. The main idea behind this is that if we would, for example, if we would like to quantize these equations and then to study, for example, for these magnetoelectrics or for TIs, the standard canonic quantization would not work well because the lattice and the interactions of the electrons have to be taken into account, and that's the reason that one has to take into account this or to bring this noise polarization and magnetization in order to quantize in a good way the electrodynamics. This framework or this formalism is called macroscopic QED, and it's well studied in the literature. That's the main idea behind this.
Okay, thank you. There's another question.
You're welcome, Eduardo.
From Alberto.
Yeah, yes, just a question or comment. In this slide, for example, you show that permittivity and permeability are functions of the frequency. So that's correct in general. But I think you did not consider in your calculation this frequency dependence, right?
No, in parts, yes, but in other parts, no. As for example, until here, it's everything taken into account.
Yeah.
But for example, when one plugs the current density here and the Green's function, everything depends on the frequencies. But until here, when one would like to obtain this angular distribution, at this point, one has to restrict for constant permittivity and constant permeability. That's from here in, and henceforth, everything works only for constant mu and constant epsilons. Before that, the steepest descent method works quite well, even though permeability and permittivity depends on the frequency explicitly.
Yeah, my point is that in principle, the velocity of the particle is important when you Fourier transform your equations. They have a restriction over the velocity, and you need ultra-relativistic velocities to see this phenomena. So maybe you have to be sure that the dispersion of permittivity allow an arbitrary velocity, in order to see this effect, right?
Right, that's also an important thing to mention. It's a good comment. To take into account epsilons and the mu's, one have to use another approach, which is called the Hamiltonian approach, which is very good explained in the Landau-Lifshitz book, but unfortunately, you have to pay some cost, some price, and the price that we have, I tried to do that, and the price that one has to pay is that one could only study this Hamiltonian approach for spherical waves, and one could not obtain the lateral waves. So it has its advantages and also its disadvantages. So that's also the thing here.
So,
but yes.
Okay. So last, so you show that even when epsilon1 is equal to epsilon2, you see transition radiation.
Right.
So in this sense, the topological parameter plays a role as a permittivity, right?
It mimics, yes, it mimics the permittivity.
Yeah,
right.
So I don't see backward cones in your plots, right?
And no, there will not appear backward. Everything is backwards in this
Yeah, I'm sorry,
in this sense, because the particle is here, and we restrict for the observer also in this part. So everything, as in this arrow, the point is the particle, and also here is the observer in this right side. So, and the particle travels in that direction. So that's the reason that both lobes are here. If one could put the observer in the other direction, so in the direction of this arrow here, but the problem would be that there will appear the cones of the Cherenkov ones, and if you let the velocity runs from taking an arbitrary value, both kinds of radiations, the Cherenkov one and this one, will interfere. That's the problem.
Okay, so because I expect a forward cone here, because so as you show in the image magnetic monopole, when you put a charge near to a topological insulator, an image charge and image monopole is induced. So when the charge moves toward the interface, an image charge is moving also toward the interface, but in the opposite direction. So I expect a forward but also a backward one.
Yes, but that depends on where the observer is. If you, for this case, the observer is only restricted to the upper layer, let's say, and therefore you could not see the cone. But if, and also here, the velocity is below the threshold of the Cherenkov radiations, as I stressed here. So therefore the Cherenkov cones are ruled out. But the main problem is that if both kinds of radiations are allowed to appear, it's quite complicated to obtain or to study the contributions of both of them. Okay. Therefore, that's the reason that we only restrict to transition radiation below the threshold.
Okay, well, thank you very much.
Oh, you're welcome, Alberto.
Okay. There's another question from Mauro.
Yes, Omar, Mauro here. So my question is very simple. I am a bit confused. When you computed the modified Fresnel coefficients, there is this parameter omega, which you painted green, but am I understanding correctly? It shouldn't be green, right? It's because green is whatever is related to new effects of the theta parameter. So it's just a typo, or I went by with the color coding.
Okay, so if you let's take the standard case, that means that delta, capital delta, it's equal 0. So here, this additional term in the numerator goes 0, and also the additional term in the denominator goes 0. Therefore, omega mu and omega mu can be cancelled. That's the reason. For example, in the first one. Also, that appears in the last one. Again, in the denominator, the delta is 0 in the standard case, I mean, and then omega can be cancelled because there's not a problem.
Okay.
And so, if you say, and in the second one, which is the crossed Fresnel coefficient, if you send delta to 0, this coefficient is equal 0.
Okay, I see. So the intertwining of the electric and magnetic say properties, the electric and permeability, not only appears in the theta terms, but also in the omega. Now I understand. Right. Okay, it's not proportional to theta, but it's an intertwining, another kind of interrelation between magnetic and electric properties.
Right. It's in comparison with when one takes epsilon, both epsilons equals or both mu's equals. In this case, the dependency on the permittivities and in the permeabilities is more intricate. Yes. So it's not so easy, and that's also the problem to carry on the integrals in an exact point of view. It's impossible to perform the integrals in the exact from just one. There's no choice. One has to perform some kind of approximations.
Okay, thank you very much.
You're welcome, Mauro.
Okay, we thank the speakers. Well, we end here the session of the talks, and we thank the speakers and the attendants, and we are going to move to the poster sessions. So thank you, Omar, and thank you again, Alfredo. Okay. And now I'm going to share a little bit just for the poster session. I will stop the recording.